positive dimension reduction, and we're going to challenge the choice of using linear decoders in favor of using something more flexible that will allow our model instead of linear subspaces. So this is where we are. And again, going back to the manifold hypothesis, again, the only hope to get ML models that work is that if indeed the problem we're dealing with has some low-dimensional structure, and oftentimes this structure could be nonlinear, so it cannot be well captured by linear subspaces. I'll show you some examples. This is sort of the definition of the operator learning problem that we have. Yeah, the microphone. And this is where we left it with DeepONets. So again, just a recap, the DeepONet receives an input function collocated in a set of measurement locations. We'll have M sensors, that is our encoder. Then we have a branch network that takes this vector in Rm and transforms it to another vector in Rn. N is the number of basis functions we're going to use to reconstruct our outputs. So now the branch network gives us. Yep. So the branch network gives us the coefficients of that basis, and then in the DeepONet we use another MLP to parameterize, which we call the trunk network, and that parameterizes a set of n basis functions tau I that will then help us to build a linear decoder for reconstructing the output functions. And I mentioned that from a dimension reduction standpoint, this model can recover functions that live on an n-dimensional linear subspace that is embedded in the ambient target output function space. All right, and we talked about the approximation theory results that told us this should work if the eigenvalues of the covariance operator in the output function space have a rapid decay. That will allows us effectively to get away with choosing a small n here and build a model. If that is not the case, of course, remember there's the universal approximation theory of Chen and Chen that told us that DeepONet can approximate anything. Yes, but this n could be prohibitively large in some cases. You might need a very, very large latent dimension in order to be able to fit things in a linear subspace. So here's an example, a very simple example where things fail and linear decoders will struggle with. And I'm just taking the simplest possible case to illustrate the issue here. A linear advection equation. So what you see here is an animation of a traveling wave from the left of the domain to the right. And what I have here is I'm taking two consecutive snapshots. One snapshot is always fixed. This is dark black line. And then the second snapshot will be this traveling wave, this gray line. And what you see here is the covariance matrix. It's a 2x2 matrix. Each entry in this matrix is computed by computing the inner product of the two snapshots, right? So the black line with itself has an inner product of 8.15. And then the black line against the gray line has an inner product. You see the number that is sort of fluctuating on the screen. And basically, you see that the inner product becomes 0 if those two waves don't overlap, right? And it becomes larger when there is an alignment or an overlap of the two snapshots. So basically, to the eyes of a measure of linear correlation, which is the covariance, those two snapshots are totally independent or are uncorrelated unless they perfectly overlap, right? So if they don't overlap, their covariance is 0. And that is really the reason that if I take now all those snapshots and I collect them and I stack them and I do a PCA or a POD on all those snapshots, temporal snapshots of this problem, and then compute the eigenvalue decay, I have the super, super slow decay. Okay, so basically that tells us that if we want to capture all the variability in this data set using a linear subspace, we need a lot of independent directions to capture that. We need at least, what is the axis here, 10, 20, 30, between 30 and 40 eigenfunctions to capture the variability of this data set. And that is precisely for all these snapshots that don't overlap with each other, we need another eigenfunction to represent that direction in this space. But this is a very kind of annoying and disturbing observation because what you see here is effectively a one-dimensional, the effective dimension is 1, it's just time, right? It's a traveling wave. all those snapshots is a one parameter family of functions parameterized by time. So the effective dimension should be 1, it should not be 30 or 40, and we should be able to compress this entire data set into a single latent dimension. The difference here is that this single latent dimension lives on a nonlinear manifold inside the ambient function space, not a linear manifold, okay? Not a linear subspace. And this is really the motivation behind using now nonlinear decoders, like revisiting this whole picture and substituting the linear choice for a nonlinear one. Is that clear? Any questions? Okay, so we're going to go back to this usual picture, which is basically the DPONet. And we're just going to throw away the linear decoder in the end. We're going to revisit the design of the decoder. And we're going to do something simple. Instead of building a linear decoder, let's just take some general nonlinear thing. So let's take a function that receives as arguments the latent code. Let's call it, before I called it coefficients of the basis, but now there's no basis anymore. So we're going to call this beta vector that lives in Rn our latent representation. It's just an n-dimensional vector. And now I'm going to build a decoder that is a function that receives this latent code and the query point where I want to make a prediction, and then return that prediction. Does that make sense? Now, f is just some general nonlinear function, and guess what? I'm going to use a neural net to parameterize it. So that will be now a nonlinear decoder. And if my data now, so a model like this should have the ability to recover data that, or output functions that concentrate on a nonlinear manifold in the ambient function space instead of a linear subspace. As long as this nonlinear manifold can be represented sufficiently by just one single global coordinate chart. So essentially this decoder is learning the inverse of a coordinate chart on the manifold. So if the manifold can be represented by one coordinate chart, then having one decoder is sufficient to capture it with, sufficiently, with the correct choice of n here. Well, of course, we should choose the latent dimension to be sufficiently large, but certainly less than the latent dimension needed by a linear decoder. Questions? All right, so just a simple choice. Throw away linear decoder, put in a nonlinear decoder, and now it's deep learning time, right? You can let's see how we parameterize this nonlinear decoder. So I don't know, can you see, is there a lot of reflection on the screen, or maybe, the curtain? All right, better. Okay, so here's again this encoder-decoder picture that we're used to. Forget about the choices I'm making on the encoder side. This is just some of my favorite choices, but it doesn't have to be. So my encoder here is, again, a wavelet projection. So basically, this beta is the latent code, is basically the output of composing the encoder and the approximating maps. That takes us to Rn. So let's call those the latent coordinates. Again, y is the query location of the output function. Sometimes I might use something called the positional encoding. And again, I think I mentioned in the previous sections that MLPs have a hard time approximating high-frequency outputs. So using something called a positional encoding or Fourier feature embedding helps with that. But anyways, gamma of y could be also the identity. You don't have to worry too much about it. And then finally, what we care about is predicting the output function s evaluated at y, and we're going to do so by building some nonlinear decoder f, some generalized decoder that acts on the latent code and the query point, and then gives us an output. Okay? So what is the simplest choice one can make as an architecture for a nonlinear decoder? Well, take your latent code beta, take your query point, or the positional encoding of your query point, concatenate them, and feed them through an MLP. Okay, that's a very simple choice one can make. Just basically stack them and feed them through an MLP. The MLP gives you an output S, and that's the function value at the query point Y. But nothing limits us there. We can start now exploring a whole bunch of options. In fact, people in other domains like computer vision have come up with alternative ways of conditioning a decoder on auxiliary information. So basically, think about your decoder being a function, S, that I can evaluate in query points Y. And the whole name of the game now is how do I take this function, represented by neural net, and I modulate it based on external input information. So now I have this latent code beta that is going to change from example to example. How should this latent code modulate the weights of that decoder network for the different inputs that I'm feeding through my operator? So the simplest architecture is this, but then folks in machine learning have come up with other exotic choices. Here's another architecture for a decoder, which people call a hypernetwork. So basically, again, you have this base network. Later on, I'm going to start calling this the base field, which is my decoder. Again, it's a queryable function. You give me a query point, I return the output. But now the weights of this MLP, or the weights and the biases, will be a function of the latent code. I'll have an additional network that I call the hypernetwork that takes the latent code as an input and spits out the weights and the biases of the base field. So that's something called a hypernetwork in the machine learning literature, and it's just a different way, or one of the possible ways of conditioning this base field on external information. Okay? Just an architecture choice. You can try it and see if it works. But then really that opens up a lot of possibilities of how you can do this conditioning, right? Where you're not limited. Things can get exotic. You can, now everybody's using transformers. You can think of cross-attention type of blocks to build a decoder. That could be another choice. And that will also allow you to have multiple latent codes. I'll show you examples later on of why that could be the case. Or yeah, you can do a whole bunch of things. I'm not going to go into the details, but this is to say that this is now becomes deep learning, and you can be creative in how you build your decoder. Okay, so here's an example that is a hyperbolic PDE. So heavily advection dominated, like purely advection dominated, in which model order reduction tools usually would suffer from. And I'll show you the effect of linear versus nonlinear decoders in this setting. So this is a shallow water equation. So you have 3 state variables. Like so essentially what happens here is you have a drop of water, you let it drop, it hits the surface, and then you have all this wave propagation going on in the domain, and then you have reflection at the boundaries of the domain. So the solution can get pretty complicated after you get these reflections. And it's a hyperbolic PDE, and now our goal is to learn an operator that maps random initial conditions of this system to the full space-time solution at later times. So you give me a distribution of initial conditions. Basically, the initial conditions are determined by the location of the drop and the height of the drop. So 3 variables. And then you would expect that the effective dimensionality of this problem should be 3, right? Because all the variability of the outputs is generated by changing those 3 variables. So this is the initial conditions, and of course we're learning a map from functions to functions. So then the space of initial conditions is the functions corresponding to this initial state, and then we want to learn the map to the full space-time solution of that PDE. So we're going to take a classical solver, sample a bunch of initial conditions, generate ground truth solutions, split them into a training and a test data set. We're going to use the training set to train a bunch of different neural operators, and then we're going to compare their accuracy on the test set. All right, so we have a couple of different models that we played with. So let's start with the top left plot, and that shows the relative L2 error averaged over all examples in the test data set between a neural operator that uses a nonlinear decoder and a very simple concatenation type decoder, like the first sketch that I showed you. So take beta concatenated with Y and just go through an MLP. That is what I call NOMAD here, versus the DeepONet. So a DeepONet is what I call a linear decoder. It's the same exact architecture, but now using a linear decoder. So basically that is a DeepONet. And you see now that the relative L2 error on the test dataset as a function of the latent dimension. You remember this latent code lives in Rn. So n is the effective latent dimension of the model. And we know that for this problem, the effective latent dimension should be down to 3, because we only had 3 parameters to generate those initial conditions. And you see that the model with a nonlinear decoder, even with a very small latent dimension, it does pretty well. And then the Y scale is in log scale, so the difference between the 2 curves is quite amplified. So this is a relative error for the 3 different variables, solution variables. All right, so that basically indicates the benefits of using a nonlinear decoder in this setting compared to the DeepONet. And on the table, you see a more general comparison between other operator learning architectures, including the Fourier neural operator, again, the DeepONet. LOCA is another architecture we had developed that was using some type of attention mechanism, but forget about it for now. The take-home message here is that this NOMAD architecture, which is basically a DeepONet with a nonlinear decoder, can give you near state-of-the-art performance, but the main message is here. You can reach that performance with a latent dimension that's an order of magnitude smaller compared to the other models, because the other models have to use a linear decoder, and this data set doesn't fit in a linear subspace. You have to bump up the dimension of that linear subspace to capture everything. And of course, because you get away with a smaller latent dimension, the resulting number of trainable parameters is an order of magnitude less, and then the training time is also faster as a consequence. So this is just an example of the benefits of adopting this geometric viewpoint and the benefit of using a nonlinear decoder in cases where it matters. Of course, there's other examples where the eigenvalue decay is fast and a DeepONet would work great out of the box. But there is no reason why you should use that in the sense like you can just substitute your trunk network with a nonlinear decoder, and that should never hurt you. It can only benefit you. Questions? Yeah.
Is there any error accumulation here? No, because you map initial conditions
to the full state, the full space-time solution. Yeah. So you see here, yeah.
And there's also evaluated over.
Yeah, exactly. Yeah, exactly. So yeah, you see some example. So I think this is sort of the most accurate example in the test data set. So you see one of the state variables plotted, and the color map is the pointwise error. And then this is the worst example in the test data set, and you see there's some error up here in the corner. And then the average error and some random example from the test set. But yeah, this is the full space-time solution. Other questions? Yeah.
Behavior general for hyperbolic PDs.
So the machine learning model is agnostic where the data came from, right? It doesn't care whether it was generated by hyperbolic PD or something else. But the property of having slow eigenvalue decay is known to be a characteristic of advection-dominated systems. And I showed you, I did try to demonstrate that through the simplest example I can come up with, which is this tau advection problem. You can sort of shows you why this happens, right? Yeah, we have more examples. Actually, that was a NeurIPS paper that introduces this nonlinear decoder stuff. So we have more examples in that paper if you want to see different cases. Yep. Yep.
Where an order of magnitude less training parameters and 50 times less basis functions, like a latex space direction, right?
Sorry?
So, if you compare NOMAD with LOCA or
yeah.
people, you have an order of magnitude less training parameters and 50 times less, I would say, number of basis functions, but in the case of NOMAD, it's more like latex, right?
Yeah.
But the cost is not one order of magnitude or something like that.
Yeah.
So it is lower, but maybe bigger than I would expect. That's why
I think for this example is a toy example. All those models are relatively small models, and GPUs are fast. So it's not like none of these models is really saturating the GPU performance in any way. So maybe deploying this in something more challenging where it's actually expensive to train, you could see bigger improvement in the computational cost. But yeah, this is sort of like a toy example. All those models you see, the most expensive model took 15 minutes to train or something, which is nothing for deep learning standards. Other questions? Okay, so I can continue. So this is the time that I was planning to talk about physics-informed stuff, but we went through it. So what I will do, maybe before No, I have a few more slides. Okay, going back now, this is the main picture. And again, this is my viewpoint of interpreting these models through a dimension reduction intuition. And again, this is a general framework. You have encoder, you have the decoder, and you compress through a latent space. So you can even think of using this type of tools to build autoencoders, right? You could have basically a single data set that you want to compress, and you can build functional autoencoders if you're dealing with functional data. So you have all the tools in place to do that if you wish. Take this data set of functions, compress it into a finite dimensional latent space, and then reconstruct and try to predict the input function. And that would be a deterministic autoencoder. And you see now that Z is my latent code that the encoder produces. And of course, you can ask the question: how do things look like in the latent space? Is there any structure in the latent space? Can I impose some structure? And one way of imposing structure in the latent space is to regularize the latent space in certain ways. And why not make it look like make the latent codes look like samples of a Gaussian? And then we can just turn this into a generative model. We can turn this into a variational autoencoder by placing a prior distribution on the latent space. So in addition now to just encoding our function and reconstructing it, a generative model will allow us to build a model for the marginal distribution of our functions, right? We're going to try to approximate somehow this P of U. And the mathematicians in this room might start throwing tomatoes because, what does it mean to have a probability density on a function space? That is not something that is not well defined. Basically, we're learning some probability measure now. It's like U becomes a stochastic process. So we're learning a generative model for stochastic processes. But this sketch sort of illustrates the main idea, right? So instead of having deterministic maps for the encoder and the decoder, we're going to turn this into a variational autoencoder. We're going to place a Gaussian prior on the latent space, very similarly to what VAs do. And essentially now, you will have an encoder that takes an input function, outputs a mean and a covariance for the latent variables. So this distribution Q of U of Z given U is a Gaussian with a mean and a covariance generated by the encoder. We're going to sample this Gaussian distribution to get a latent code through the reparameterization trick, take the latent code, push it through the decoder, and get a functional sample in the output. And now, because we have this fact of being able to sample in the latent space, this becomes a generative model. We can just sample latent codes and decode them, and we get a whole distribution over U's. So essentially, we have a generative model of this form, right? So the P of U, quote-unquote, density is represented as a mixtured model over this latent, the latent codes. So there are some technicalities. I was planning maybe to cover those tomorrow if you're interested in how you actually train this. Because moving again from finite dimensions to function spaces, there are some mathematical technicalities on how you build objective functions for training variational autoencoders. You have to be a little careful there. But I could leave that for tomorrow to go in more if people think that's an interesting topic to discuss, sort of generative models in function spaces. Okay. All right, so I think that's all for now. And maybe I can conclude, since I'm taking this dimension reduction viewpoint, I have this chart that maybe kind of gives you a taxonomy of different things. And there's two regions in this chart. So let's just focus now, forget about this axis for a bit. Let's just focus on the top part. And this is all you already know from the finite dimensional setting. So these are techniques for doing dimension reduction in finite dimensions. So things like principal component analysis, autoencoders, variational autoencoders, kernel PCA, diffusion maps, blah, blah, blah. And all these tools operate on vector value data, right, on discretized data. And therefore, they're depending on the discretization. And if you want to query them, you have to also constrain yourself to that initial discretization. And essentially, all these techniques learn some function that maps between vector spaces, from some latent space to some output space. What I showed you now, or the last couple of hours was this setting where now we're working with functional data. So we do not discretize first. We allow the data to live in a function space. By doing that, we have models that are discretization invariant. We can query them continuously at any query point that we want. And we're no longer learning functions between vector spaces, but we're using neural nets to parameterize operators between function spaces. And you can extend pretty much these techniques to the functional setting. So you can have DeepNets, you can have functional versions of PCA, you can have functional versions of reproducing kernel Hilbert space methods, the Fourier neural operator, the Nomad method I just showed you. The BANOP is this variational autoencoder part that I can show you tomorrow. So that's sort of like the finite dimensional versus infinite dimensional data. And now maybe the vertical axis is slightly more interesting. So all these methods now are purely data-driven, purely supervised. You just need data to make them work. But then there is this physics-informed part on the bottom part of the chart, where people coming from the reduced order modeling community, essentially this is what they do. They do dimension reduction, which is sort of physics-based, right? You take a PDE, you plug in a reduced representation, you project things down to a basis, you get evolution equations for your latent degrees of freedom, and you come up with linear techniques for dimension reduction, like a POD-Galerkin method or projection-based ROMs. The vast majority of them, at least until deep learning became popular, were based on linear dimension reduction techniques. Of course, now everyone is wearing a deep learning hat, and people are trying to build autoencoders and LSTMs and all those things. These are all discretized first, right? So you discretize, you have a finite number of degrees of freedom, you feed them into an autoencoder, get a reduced representation, maybe have a recurrent network to learn dynamics, and that's sort of kind of what is this data-driven community of model reduction doing these days. And on the other hand, you have the infinite dimensional setting that you don't discretize first. And this is where all this physics-informed DeepNet and the physics-informed Fourier neural operator stuff lives. So again, now you have evolution equations, but you're actually using the actual PD without any reduction as a constraint to build those models. So that's kind of a very high-level taxonomy that I have in my head in terms of the different methods. Yeah.
The evaluation of inputs, functions, and sensor points, some way of discretization.
Yeah, but that's just a choice. You can substitute it with a different type of encoding that does not have that limitation, right? So that was just the DeepNet version 1, but that's just a choice of a encoder. You can swap that with something else that is discretization invariant. But yeah, I'm putting this slide up because I know probably a lot of you have background in reduced order modeling, and the message I have is that we're all talking about the same thing, but there's different communities, right? But if you adopt this dimension reduction viewpoint to interpret what the deep learning methods do, there is a meeting point between the two communities. And the meeting point is like when you make the decision to switch from linear representations to nonlinear and start using neural nets. Of course, you lose all the theoretical guarantees and the ability to do math in that setting. All right, other questions? Let me see the chat also, because there was a question in the chat earlier. I don't know if there is any activity online. Nope. All right, so then there's no break, so I'm going to continue to the next topic, and I have a feeling that might take us a little longer. So let me move on to part 4. So going back to the recap. Oh, I think I kind of messed up a little bit, sorry. Let me do some online debugging. So basically, this slide should be here. Okay, so we talk about DeepNets, we talk about FNOs. Part 3 was about this nonlinear decoders part, and that was my viewpoint on dimension reduction. And I'm going to take a totally different viewpoint, which is the computer vision viewpoint in all of those things. Because over the last couple of months, I realized that everything we're doing has already been done by the computer vision folks, especially when we limit ourselves to kind of square domains and image-to-image type of prediction tasks. So I'm going to take a step back, and we're going to take a trip to a parallel universe of computer vision and see what people have been doing there and come up to the realization that we're all doing the same thing when it comes to operator learning. So quick recap, discretize first versus discretize later kind of came up a couple of times. I'm not going to spend too much time on that. But yeah, in the context of PDEs, typically you will discretize. If you want to build a neural operator that maps from inputs to outputs, you would have to discretize your initial boundary condition or whatever inputs you have. Also discretize the PDE solution on a grid. And then you would build a neural net that maps between these finite dimensional spaces. Could be a convolutional net, a graph net. In any way, it's an architecture that operates on finite dimensional data. And therefore, it will be fundamentally mesh-based, and it will be restricted by the initial choice you make on your discretization. And then at test time, if you need to accommodate data of different resolution, you will have to rebuild the model and retrain. And if you want to evaluate it at new query points, you would have to interpolate. The discretize later viewpoint says, okay, let's live in function spaces. Let's not make choices about discretization from the get-go. Let's build models that can accept functional data of whatever resolution. And then the resolution and the number of measurements just becomes a consequence later on when we're training the model. It's not part of the model design. Okay, so here's again the definition of the problem. We've seen it again. So we saw some architectures. And let me now take a step back and then talk about neural fields. So this is what people in computer vision are calling this kind of models. They're not calling them neural operators. So what is a neural field? Well, neural field is just a function that is defined on a continuous coordinate domain. It's just a continuous function, f from some domain D that returns vector valued outputs in our case. So D could be a spatial domain again, could be a spatial temporal domain. It's just a domain that we can continuously query and get a vector valued output, like a velocity field or temperature and so forth. And we're going to call this a neural field because we're going to parameterize this function by a neural network, a coordinate-based neural network that receives query points and returns the function value at those query points. So this is a neural field according to the computer vision jargon. So neural fields encode signals defined over some input domain into the parameters of a neural network. Because in a little bit, I'll show you that the goal of the neural fields is not to approximate a single function, a single signal, but actually encode multiple signals at once in a single neural net. And those are extensively used in recent literature in computer vision, the last 5 to 6 years, probably before our community became interested in neural operators. Coordinates for them typically represent positions in space, like 3 x, y, z coordinates in space or time, viewing angles, and so forth. And there is actually a very nice review paper on neural fields. There have been big workshops and big machine learning conferences and computer graphics conferences. So it's a very active field, probably a lot more active than the neural operator field in the scientific computing community. So here's some examples of neural fields. On the top, you have an Eulerian flow field of a fluid. So you have the inputs to your coordinate-based MLP is a position in space, x, y coordinates, and the outputs are u velocity, v velocity, and pressure maybe. So you have a vector-valued output, or u and v velocity. So the input lives in R2, and the output is a vector in R2. There's another example in computer vision, a signed distance function that basically measures the distance of different points from some predefined boundary. So the input, again, is a point in 3D space, x, y, z, and the output is the value of that signed distance function. So it's a function that is 0 on the boundary, and it has positive values outside of the object of the shape there and negative values inside the shape. So you see the contours of that function. And then finally, another example in geospatial data, again, in 2D, you have some query point somewhere on the map, and then you have n outputs for that query point. Could be, pressure, temperature, humidity, CO2 concentration, a bunch of variables, for instance. And these are continuous neural fields in the sense that you can query those functions anywhere you want in space, right? Or anywhere you want in their input domain. So the benefits of neural fields is that they can create outputs at arbitrary resolutions just because we can query them anywhere we want. They are continuous functions. We can query them at arbitrary resolutions. And they're memory-efficient representations of high-resolution signals and high-resolution scenes. So people in computer vision have used those to solve tasks like view synthesis, rendering of complex scenes. So this whole business of neural radiance fields or NeRFs has been very popular and successful in the rendering community. They have been used also for shape representation, so learning things like shape distance functions to represent three-dimensional shapes and complex geometries. So yeah, there's been a lot of activity in the vision community in using neural fields the last 5 years. Now, the interesting thing that this community has introduced, and it kind of resonates with some things we saw already with DeepOnNets and FNOs, is they have come up with these ways of conditioning neural network architectures on information. So let me come to this slide in a second. And let me first introduce what do I mean by conditioning and what is a conditioned neural field. So far I just showed you a neural field as being a function that takes x and y coordinates and gives you a function value. But the whole objective here is to encode multiple signals simultaneously in one model, in one architecture, without having to retrain or adjust the weights of the model. And that is done by conditioning on some external information. You have your query point, so F is your neural field, Y is the point that you want to query at, but then there's some latent code that is also an input that could correspond, well, in vision could be a different view angle, it could be a different texture or something like that. You can also see where things are going. Now Z in operator learning could be an encoding of your input function. But the whole name of the game is how do you condition this base field, this base neural field, on this additional input Z. And that is what will allow you to encode multiple signals. So each signal will be a different Z, and you will use a single architecture to encode those multiple things. So this is the picture to keep in mind. This is your base field. This is your neural field. This is a continuous function, query points, outputs. And now the question is, how do I condition the weights of this network on the Z's, on the external information? And people in vision use that type of stuff to incorporate additional semantic information like the object class, the color of a scene, the texture, view angle, and so forth. And what they have been really good at doing is they have come up with smart ways of taking a base neural network and designing effective conditioning mechanisms for incorporating this Z information into the weights of the network. And there's two general classes of conditioning mechanisms. There's the global conditioning, in which essentially the conditioning variable Z is independent of the query point. So Z contains some global information that is concatenated, let's say, to the query point and then passed through the base field. And concatenation is one way of conditioning, like we saw in our decoders earlier, but there could be other ways of doing that conditioning, like a hypernetwork or something else. But the message here is that in global conditioning, Z carries global information that is not dependent on the specific query point Y. Whereas in the local conditioning, the conditioning variable is also a function of the query point Y. And I'm giving some examples here, but don't worry too much about the architecture choices. There are some examples that people have used in the vision community to model occupancy fields or radiance fields and things like that, things that they are interested in. But now keep in mind these two mechanisms, because these we're going to interpret everything we've seen so far through the lens of global and local conditioning. All right, so let's see. This is what operator learning does as well. The same picture holds for all the models that I showed you so far. The goal of operator learning is to build, again, a queryable function S from some input function U, right? So we have our base field, and we want to somehow condition our base field on the input function, the information coming from the input function U. It looks like the same thing. And yeah, all right, so let's see that indeed is the same thing, and we can see that through the architectures we saw so far. So here's the DeepOnNet. This is what you saw so far. There's a picture from Lulu's paper, branch network, track network. Then I gave you this encoder-decoder interpretation earlier with basis functions and things like that. Well, now this is the neural fields interpretation. This is our base field, which is kind of our decoder. It takes as input the query point. It outputs the output function evaluated at the query point. And the conditioning mechanism that the DPONet employs is that the input function is going to be modulating the last layer of the decoder, right? So whatever sits in the last layer of this MLP is the basis functions. And remember, we take a dot product of the basis functions with the coefficients to get the output. So basically, this last linear layer is determined by the coefficients that your branch network generates. So essentially, what you have is a base field, and you have a global conditioning mechanism. You have your whole input function globally entering your encoder or your branch net. And the branch net gives you the weights of this last linear layer of your decoder. This is a different viewpoint of looking at the DPONet. Does it make sense? So that's the DPONet. It's a neural field with a global conditioning mechanism where the input function only modulates the last layer of the decoder. All right? Good. This is what the Nomad architecture does, which is very similar to DPONet, but now we switch the linear with a nonlinear decoder, right? Very similar viewpoint, but now since, again, we are only using global conditioning, so we take the entire input function, goes through the encoder, gives us a latent code, but now we take that latent code and we concatenate it with a query point in the Nomad case. And by concatenating it with a query point, then it effectively modulates all the weights in the decoder, not just the last hidden layer weights like the DPONet, but the entire decoder. That could be if we were choosing to concatenate the latent code. If we were to use a hypernetwork, same story, right? The latent code goes into the hypernet, and the hypernet globally modulates the weights of the decoder. That could be a different design of a nonlinear decoder. But summary, this is a neural field purely using global conditioning, where now information of the input function modulates all the weights in the decoder in some way. Clear? All right, the FNO has a more delicate interpretation as a neural field, but it is a neural field, so let me walk you through it. So here's the FNO. Remember now the layer, this is the FNO layer. The FNO layer has two components, has this pointwise multiplication part and the kernel integral transform that we approximate using the FFT. Now I'm going to massage this a little bit just to make it look like a neural field. So I'm going to take the FFT part, and I'm just going to use Euler's formula to write it down instead of complex things. I'm going to write it down as sines and cosines. So we have the real part of the FFT coefficients hitting the cosines minus the imaginary part of the coefficients using this hitting the sines. This is basically this term, right? The kernel integral transform. So I can rewrite the FNO layer in this notation now. Z is just a function that picks the real or the imaginary part of the Fourier coefficients. So this is the same thing as the top line, just rewriting the FNO layer in this form, because that will allow me to interpret it as a neural field in the next slide. Is that okay for now? All right, so here's what the FNO does. First of all, the FNO has both local and global conditioning mechanisms. So the first term here, this W matrix hitting pointwise the input function evaluated at Y, is local. It depends on the query point, right? So you give me a query point, I evaluate U, and then I hit it with W, that will give me a latent code a Z that is locally dependent on Y. So that's the local conditioning via adding this position-dependent bias. So you can think of this term as a bias, right? Now, the global conditioning is as follows. So at the end of the day, you can think of the FNO layer as an MLP. It's a very, very simple MLP. In fact, it's an MLP that takes the query point as input. It has no hidden layers whatsoever. The only thing that it has is a set of positional encodings, gamma. These gammas are sines and cosines. So this is the formula to keep in mind. I have it also in the previous slide. So you can see these gammas of y's are the sines and the cosines. So if you look, this term here is basically rewriting this equation, right? So z of ku picks up the real or the imaginary part, and gamma of y is the cosine and the sine part. So the FNO layer is just a very, very simple network that takes a query point, does this positional encoding on a set of fixed frequencies, okay? And then it modulates this last linear part using the real and the imaginary Fourier coefficients, similar to how the DPONet was modulating the last layer of the decoder using the trunknet. Here, the modulation is done through the real and the imaginary part of the Fourier transform. This is this term, and then you add to that the local conditioning. So this part is doing global conditioning. It carries global information about the input function. And this part is doing local conditioning. You add them together, pass them through a nonlinearity, and that gives you an FNO block. So it's kind of an extremely simple MLP with very little trainable parameters, right? The only trainable parameter is this W matrix and this K matrix that hits the Fourier coefficients. There's no hidden layers or anything else. So yeah, that's sort of like a neural field viewpoint of what the FNO layer looks like. Is that clear? Should I try to repeat anything? I know it's a little bit more complicated than the previous cases, but it is an exact interpretation of what an FNO does as a neural, through the lens of a neural field. So there's a base field. Again, the base field is basically a queryable function. You give it query point, it returns the output. The base field is simply just a positional encoding, like it's just a single layer network in which in the neurons you just have sines and cosines of different frequencies. And now you're going to linearly combine those sines and cosines, and the weights of this linear combination are basically the coefficients you get from the FFT. So what I call by modulation of the last linear layer is these weights that determine how the sines and the cosines are linearly combined to give you the output.
But then you stick more of them.
Yeah. Then you make it deep, basically, yeah. But a single block is a neural field. Huh?
So no more of the bias.
This bias will always be local because it's always evaluated at the query point Y, right? This part is local. So it's purely local and purely global.
Sorry, about the global conditioning, why appears also there, but we don't consider that as local because Y appears in the basis function, not in the trainable ways. That's why.
Yeah, so here I'm calling this global conditioning because it uses global information about the input function. So this U here, you have the whole input function, and you do an FFT on it, and you get these coefficients you had. So that carries information globally about the input function. Whereas this term just evaluates the input function at the query point Y, so it just locally evaluates the input. Yeah?
Yeah, the possibility to use trainable filters rather than Fourier filters.
Yeah, that could be a different architecture, yes. Yeah, and then that's sort of where I'm heading towards, but yeah. Yeah. All right, so the FNO is also a neural field. At least the FNO, the single block of the FNO is a neural field, and then, okay, you can have this, I don't know how we can call it recurrent conditioning. If we stack more layers, I don't know, we can come up with a name for it, but yeah, that's it. All right, so that's my unifying viewpoint. All existing neural operator architectures in our literature can be implemented with 4 lines of code. Of course, there's a little bit of complexity behind that, but all they do is they take an input function, they take a query point, they generate some latent code through a conditioner module that processes the input function and the query point. And then you have a base field that receives a query point and that latent code. So that latent code somehow modulates this base field and gives you the output function. So if you're thinking about how I'm going to code all those things up in a unifying way, using this class gives you a starting point to build FNOs, DPONets, and whatever other model is out there. Of course, all the complexity is now hidden in exactly how do you implement the conditioner and the base field. But that's sort of like the unifying scheme here. Okay.
The FNO case is not the whole new network, multiple objects of the class CNN.
Yeah, exactly. So basically, this will give you one block of the FNO, and then you can compose the blocks to make a whole architecture. Yeah. Good point. Other questions? All right. So why use DeepONets and FNOs to begin with? Like the people in the vision community have done a lot of work in building very powerful architectures for doing all sorts of conditioning. So here's a model called the Scene Representation Transformer, used in Vision for scene representation tasks. It's probably one of the state-of-the-art models a year ago. Maybe it's outdated by now. It's a model for kind of view synthesis and scene representation, but maybe now it already kind of looks familiar to you in the sense that here's a base field. This is our decoder. It takes as input a query point and gives you an output. And now this base field is going to be modulated, or parts of this base field will be modulated by information coming from an encoder part or a conditioner part. So now the encoder in this case takes images, runs some kind of convolutions, fetches the features of the convolution layers at different levels of the convolution hierarchy. These become tokens. This become a sequence of tokens that are fed into a transformer module that processes sequence of tokens. So that's a transformer backbone that also spits out a processed sequence of tokens. And now the decoder is a cross-attention transformer that processes these latent tokens and the query point to give you predictions. So that's like, okay, it's a big deep learning architecture that it falls under the same viewpoint that I just described. It doesn't use FNO layers. It's not a DeepONet. It's something that it looks like a lot more powerful. And now is the point where people, you can get creative. So let me show you an example that is a sort of an extreme simplification of this architecture. Like it draws some motivation and ideas of how this architecture works, but we're going to try to overly simplify it. And then I'm going to show you that overly simplified architecture gets state-of-the-art results in challenging operator learning benchmarks compared to DeepONets or FNOs or other stuff. But before I do that, let me also say that why limit ourselves to purely local or purely global conditioning mechanisms? There's a whole continuous spectrum between that, and we can think about conditioning on information at multiple scales, not just purely local or purely global. So, the pointwise connection, the pointwise operation, the FNO carries this WU of Y part in FNO carries pointwise information, then the kernel integral transform or the branch net in the DeepONet carry purely global information, but one can come up with easy ways of incorporating intermediate levels of locality in this conditioning. So here's a very simple encoder module that we can use for building an architecture. So let's say we're dealing with an image-to-image regression task, or like we have functions that live in a 2D domain in the input and the output. Here's a simple architecture. You take your input function U, and you feed it through a convolutional backbone. So the first layer of the convolution will extract local features, and you'll have a small number of channels. And as you stack more layers in this convolutional network, you will extract more abstract, higher level features. So local features, more global, more global, more global, maybe all the way to global features at the very end. And then I can take those features at each level of this CNN hierarchy, maybe transform them a bit so they have the same dimension, the same latent dimension. And now I have a sequence of tokens, each one containing features from every level in this CNN hierarchy. So that is basically now a multi-scale representation. And I should mention, we also have a query point. So for a given query point, I can interpolate the CNN features at these query points, because otherwise these feature maps will be very, very large to process. So a simple way to reduce that is I take the query point, I interpolate my CNN features, and that gives me these different latent codes. So these different latent codes are the interpolated features at every level of the CNN hierarchy. And they all have the same dimension. And each one of these latent vectors contains information at a different scale, from a very local scale to a very global scale. So you have basically multiple scales in this case. In other ways, I took an image and I converted it into a sequence of tokens locally by looking at local neighborhoods around my query point. So I have a query point. The first layer of the CNN is going to look at a very local set of features close to my query point, and it gives me this first set of tokens. The second layer is going to look at a larger neighborhood around the query point and generate features that live in the second token, so on and so forth. At the top of the CNN hierarchy, I will get, because as I stack CNN layers, my receptive field increases, whatever sits here is going to carry more global information about the input image. So I have a sequence of latent codes that contain local to global information progressively. And I'm going to take this sequence of latent codes, and also I'm going to take again my query point. So this red box is essentially that query point is also fed. And I'm going to build a decoder that performs a cross-attention operation between this sequence of tokens, and this sequence of tokens are functions of the query point. So this is, in some sense, well, it's not purely local, it's not purely global, right? It's multi-scale conditioning. And I'm going to do cross-attention between my latent sequence of tokens and my query point. So I feed that into like a multi-head self-attention, like basically a cross-attention transformer block. Maybe 1, 2, 3 blocks of that. That's a hyperparameter choice. And then finally, you'll have some MLP that takes everything and projects everything down to the output dimension that you want. So here's an architecture, which is not an FNO, it's not a DeepONet. It's very, very different than either of those two things, but it's a neural field and is inspired by things that people do in computer vision. So how does it work? So we took one of the benchmarks. Well, actually, this is work in progress. So we're trying to submit this to ICLR, which has a deadline in 10 days or something. We took a benchmark from the PDE Arena suite that my colleagues at Microsoft have developed. And this is a benchmark, this is a toy weather modeling problem. So this is basically a PD system governed by the shallow water equations on the Earth. And it contains PD solution fields of vorticity and pressure variables. The resolution, now if you view them as images, this is 192 by 96 on a Gaussian grid on the surface of the Earth. And now our goal is to take the state of the system today and predict the state 48 hours later. So want to do this temporal prediction. So the training data set contains 5,600 pairs of examples of state today and state t plus delta t. And we're going to train different neural operator models on this benchmark and see how they do. And the current state of the art for this benchmark reported in the literature is achieved using UNet models. So classical computer vision, discretized first, image-to-image regression. This is the state of the art in terms of performance. And you can see that the fields are not very simple. There's, the vorticity field is quite turbulent, and the pressure field is also quite complicated. So here's some very, very preliminary results. This is still work in progress, but basically this multi-res neural field just worked out of the box. It gets error, relative L2 test error that is competitive with the UNets, actually a little bit better than the UNets. It's 3 times better than the FNO in terms of accuracy, and I don't know, like 2 orders of magnitude better than the DeepONet in this case. This is a very, very complicated benchmark. So DeepONets struggle a lot. Also, in terms of size, we're now starting to talk about deep learning. These are models that measure in the millions of trainable parameters. And in fact, now I'm doing my sabbatical at Microsoft, and we're looking at billion parameter scale models for this type of tasks. What you see here is visualizations of examples in the test data set, so vorticity fields in the test data set. So we have 5 different samples. On the top row is the ground truth vorticity field. In the middle panel is the prediction, which you can reconstruct at any resolution because we have this neural field queryable. We can, try to do super resolution if we want it. And then the bottom, you have the pointwise error. And these are all examples that were not seen by the model during training. And you see there's a lot of variability and complexity in those fields. Questions? Yeah.
I don't know if it's a very complex problem. If you solve like the ground truth with a finite element solver, we have an idea on the order of magnitude of the error that's committed on like the
So I should say that the ground truth data is generated indeed using, I believe, a spectral element solver or a spectral method.
Okay.
Yeah.
Would you have an error bound on this? Like, is it very high because it's a hard problem, or very accurate?
I mean, the ground truth is a numerical prediction, right? So that would take it as ground truth.
Yeah, but did you do like, I don't know, like a multi-level study to see like how far the numerical solution is from the real solution?
I think maybe you're asking if we've done some kind of mesh refinement with the numerical solver to make sure. Yeah, the numerical solver we consider as a ground truth. Yeah, it's a converged, clean, accurate solution with a high order numerical method. So that we take it as for granted.
Like how does this error compares to those kind of L2 error? Are you of the order of?
So the error of the ground truth solver is 0, basically, because that's what we're using as a reference.
Yeah, but like if I would, as someone like run this model, like a high performance computing with like very fine elements.
Yeah.
Versus like how can I?
Yeah, that's something
we have an error estimate on this.
No, that's something we haven't done. But
see, like because it's hard for them, so maybe this kind of error is good even for like an FE solver.
Yeah, so what I'm reporting here is I take the classical numerical solver at this resolution, use that as a ground truth, and I'm comparing, and also I didn't do those simulations, but I assume they have done some mesh refinement study and concluded that this resolution is sufficient for resolving the system. So I take this as a ground truth and I compare the predictions of the ML models at the same resolution with this ground truth. And basically what you see here is a relative L2 error, meaning that this number should be interpreted that the DeepONet has a 62% error against the ground truth, whereas these models have a 0.3 or 0.4 percent error against the ground truth. Again, this is all very preliminary results, but this is just to show that, study the computer vision literature, borrow ideas from what they've done. You don't need to, over the last few years, there's a lot of like tension of DeepONets, FNOs, who's better, who's worse, who cares? So just, there's a lot more you can do. And this is another example that we kind of, because referee number 2 is going to say, why don't you discretize first? And units are great. We're doing this comparison against the units on a super resolution prediction task, namely that we're going to start from coarse resolution data. So we're going to half the resolution and train on coarse resolution data, but then try to do super resolution with our model versus the unit. In the unit, you just do it by running some kind of bilinear interpolation. Our model inherently supports that. And that's an interesting question, because essentially our model is doing some interpolation built in. How does that compare to training a unit and then interpolating later, right? So you see that if this is the training error of the state-of-the-art unit versus us, comparable. This is the error that you get if you interpolate both models using bilinear interpolation, again, comparable. But this is now the error that we get if we use our native ability of our model to do super resolution. So essentially, this is what we get if we use bilinear interpolation on the coarse resolution to get a result versus using whatever interpolation our model came up with, to do the super resolution. And it seems that, it learned something better than bilinear interpolation in some sense. So that's one of the reasons why one may prefer to adopt a neural operator or neural field approach as opposed to to a unit or a discretized first approach. Okay, so that's what I have, and we have plenty of time for questions and discussion, I think. Or we can talk a little bit about what I was planning to present tomorrow and take, maybe, yeah, I'll leave that for later. I guess I can take questions first, yeah.
One question on slide 4. Can you say how this looks like? How you make these huge models converged? Is it converged?
For
Does
the,
it work out of the box? Or is there some
yeah, I mean, there's a little bit of playing around with hyperparameters, not to get better results, but to get a sense of how the model kind of responds to different choice of hyperparameters. But no, it sort of works out of the box, and I would say that these are not huge models by any deep learning standard. These are still, I mean, training this model takes 20 minutes on 1 or 2 GPUs. It's not, yeah, it's not a huge model by any means. Yep.
So if you want to take all of those based on just one slide, we claim that the multi-race neural field on the results of the CFD code on a concept, right?
Yeah.
So it has never seen the solution of the CFD code on the final.
Correct. Yeah.
Okay. Then if we produce a table of values, okay,
Yeah.
everybody wants that is 48, right?
Yeah.
We interpolate with the linear interpolation and we get that number.
You get this one. Yeah.
In the other case instead, we have exactly the same model. We don't replace anything. We use more query points, right?
Exactly. Yeah.
We query at the points where we run the CFD
Yeah.
code at high resolution, and then we finish. Okay.
Exactly. Yeah. Basically, that sort of tells you this model learns to do some kind of interpolation that is better than bilinear interpolation. Because there's a lot of if you talk to someone that loves units, they're going to say, why do you do linear? We can always interpolate the unit, right? But then how do you interpolate the unit? If you just do plain bilinear, you don't get something. Yeah.
Did you put some physics in the
No, no physics. This is purely data-driven. Mm-hmm. Well, it's part of the model design to be able to do that in some sense. I had another comment which I forgot on this. Oh, about how easy it is to train. The thing that we had some trouble with initially when we first implemented that, we were getting fantastic training error and crappy test error, meaning it's overfitting a lot. It has a tendency to overfit. I think that has to do with the fact that the architecture itself is kind of very powerful in approximating even these really complex solution fields. So you either need to push it to the regime of a lot of training data or do careful regularization. So the moment we added some dropouts in parts of the model, then basically it kind of worked out of the box. Yeah.
Maybe one question, because you said that this model runs on the order of a couple of minutes.
Training-wise, yeah. Yeah.
Which is very impressive in my opinion. Like, I saw that in the architecture you use parts, like transformer parts, so to speak. Do you make use of some pre-trained transformers, or do you train everything from scratch?
No, this is everything from scratch. Yeah, end-to-end. There's no pre-training fine-tuning. But that's something, that was just a toy first attempt. There is absolute merit in doing what the people in machine learning do, like pre-train the transformer and then fine-tune on different tasks. Then you can build a foundation model that can do multiple things after it's been fine-tuned. But that's something we have not really explored in this context yet. Yeah, but that's super cool. That's a great idea. I mean, that's where things are heading towards. And like also seeing what it takes, okay, because this is again a toy benchmark, but if you think about using this for, weather modeling, I don't think people in academia will be able to afford to do the pre-training. The amount of engineering that goes into the kind of amount of GPU manpower and GPU hours is just insane. So if those things end up working, it feels like, people at Google or Microsoft will be pre-training these large models, and then in academia, we'll just fine-tuning them in interesting tasks. Yep, so other questions? Yep.
About all the presentations, I didn't see like geometry change. So can those things be implemented in like a parametric design optimization?
Yeah, I have some of that to show tomorrow. I can go into this a little bit tomorrow. The answer is yes and no. Yes, in the things that we have proof of concept results for toy stuff, but then taking this and doing it for real complex geometries is still, I think, an open. Yep. These are the parameters of the neural network architecture, the weights, the biases, all the free parameters that are trained in the neural net. Oh, good question. So here the inputs are 2 time steps of the system, I think, 2 previous, like the system state. So vorticity, well, I think the input is 3 channels. Maybe I'm missing something. Certainly vorticity, pressure, and maybe something else, or those 2 channels. And then we have 2 time steps. So that system state at time t and t minus delta t. So let's say 4 channels. But each channel is a full image that has resolution 192 by 96. So kind of the dimension of the input is this number multiplied by 4. Yeah, in this case, we didn't consider any boundary conditions because the original PD system is solved on the sphere, and we just turn it into an image. But yeah, I mean, if you have a different problem where you want to learn a map from boundary conditions to something else, then yeah, that's part of the problem setup. But yeah, most of the work that has been done in this front is on this type of image-to-image regression problem. So there's certainly a lot of room for looking into things that live on more complex domains. Starting with sphere or starting with, moving to more complex geometries. That's an open problem. Yeah.
Regarding the open, you also try to reduce parameters.
You can still get overfitting even with smaller size models. But so, okay, let me think about that one. We've tried a lot of different things. So in the paper, we'll have ablation studies with respect to, data set size, model size, this kind of scaling laws. But I don't have all those things on top of my head. But overfitting was one of the main issues. Before we started regularizing, we couldn't get good test performance. The training loss was really small, but the test error was pretty bad. So yeah, some kind of regularization was required. But we never also pushed this to very large data sets. The largest data set was, this 5,600 examples. We didn't go beyond that in terms of training set size. Again, that was just like a very first attempt. Like, we kind of wrote the whole paper as, hey, let's interpret the existing models as neural fields. But then we realized, why not do, borrow things from vision and come up with this Frankenstein architecture? And it works. So, and we just jumped directly to this more challenging. I mean, we did some simple cases, and in the simple cases, it works well, but then all the other models work very well. So it's kind of, you get some marginal improvements, but okay, who cares? But in these more complicated benchmarks, and we're actually working on another benchmark with buoyancy-driven Navier-Stokes problem, which is even more complicated than this one. And I think there the gap against FNO and DeepONet probably is going to be larger. Units are still doing very well. So even for the Navier-Stokes, it's kind of the gold standard, state-of-the-art result. Yeah, we haven't tried, but I mean, in principle, yes. In practice, yeah, it will be harder to generate those data with numerical solvers, and these architectures will probably get bigger. But 3D in this case, it means that you have to come up with a different encoder. Like this 2D convolutions might need to be replaced with something else. And this query point now includes X, Y, Z instead of X, Y. So the main part that's going to change is the design of this piece of the architecture, of how you can take volume data and turn them into a sequence of tokens. I think that's now with everybody using transformers. At the end of the day, that's kind of the name of the game. This first part of the network, what I call the tokenizer, depending on whatever data modality you have, let it be 2D image, 3D image, some graph, some continuous function, how do you take that input modality and turn it into a sequence of tokens in a way that that transformation encodes multi-scale information? So the only thing that will change in the pipeline to accommodate this 3D case would be the design of this first part of the architecture. What is the proper module to process 3D data and turn them into a sequence of tokens with multi-scale information? Sorry, which one? Yeah, the CNN part is it's trainable here. Yeah. Yeah.
When I see this picture, you said that the area is the surface of an Earth. And when I see this, did you somehow use the?
Yeah, we use periodicity. Yeah. So we have periodic padding. Yeah. Yep.
Yeah, so you talked about the prefigures, the questions, and the great, but so I noticed that you were talking about how even if you have, say, X, Y as input, and then you sample out, let's say P, X, and Y for, let's say, columns. But then in this example, you just have a single prediction for P plus delta T.
Yep.
And so when you think of that, what is the rationale behind that decision? Doing a single time step versus allowing the output to be sampled input as well?
Good question. So, all right. So for short time predictions, it's okay to include time as a coordinate in your query points, or you can come up with ways of conditioning your model on this time input. Maybe it's not part of the Y vector, but maybe you can use time or embeddings of the time coordinate to condition certain parts. The way people in computer vision do that, when they want to modulate, let's say, a transformer block using some external thing, either they're going to use it as a positional encoding of the input. So in these latent vectors, they're going to add a positional encoding that depends on the time, on the delta t. Let's say you have variable delta t's, for instance. Or they're going to tweak, there's something called film encoding. So they're tweaking the layer. So this transformer block has a layer norm operation, and then you're tweaking kind of the parameters of the layer norm with that time encoding. So there's different ways of kind of injecting information into your architecture. So one way is obviously concatenated with a Y. Alternative ways is to just use these modulation tricks that the deep learning folks have come up with. And that should work fine for short times. Like you want to condition, because the longer the lead time you want to predict, the more complex the operator becomes, right? Especially for a system like this that has complex dynamics, the further you want to go into the future, the more complex it will be, or even it could be impossible if the system is chaotic, right? You may not even be able to predict. So for longer lead time predictions, probably the only hope is to train a model only on short times and then do this autoregressive type of prediction. So predict delta t ahead, take the prediction, feed it as an input, predict the next delta t, and then kind of unroll autoregressively. There's challenges there when it comes to stability, because you might quickly accumulate errors. I can talk a little bit more about that tomorrow. Yeah. Yeah.
So this example with the new encoder with these shadow waterways, this only works for a short time.
Yeah. Yeah. Yeah, it does indeed. It only works for short times. For longer times, you have more reflections from the boundaries in that example, and the solution gets more complicated. Yeah, and the performance deteriorates as you increase the time horizon. Is this related? That is just harder. Yeah, it's just it's just a harder operator to learn. Like maybe as you increase that, you need to increase the capacity of the model, and then training is more complicated. Like everything gets more complicated. Other questions? We have a little bit of time, maybe 4 or 5 minutes. Yeah. Let's see the chat. No questions on the chat. I don't know if anyone in the audience has a question. All right, maybe I can take the last few minutes. First of all, thank my students, because basically they've done the work. Really, the person who's done all this operator learning work is Jacob Seidman. Sifan is another PhD student who is doing a lot of work on the physics-informed stuff. And then some other former students that have moved on and current students that are helping out. The sponsors. And then for tomorrow, the room is open for discussion. I think this is sort of my take of what I was planning to do. In the first part, I wanted to talk a little bit about aleatory and epistemic uncertainty quantification with this type of neural operator models, because I think that's sort of a theme that comes up frequently, especially when we're thinking about using these tools for engineering problems and design optimization problems. And in the last part, I would just give you some highlights on applications. So neural PD solvers, I would touch on this long time rollouts issue and show some recent work there. We can talk more about physics-informed stuff and all the tricks that goes into making things work. An interesting part is using these tools for Bayesian optimization and active learning with high-dimensional data, because so far people use Bayesian optimization for design, but usually confine themselves into Gaussian process surrogates, and those don't scale to higher dimensional data modalities. And I have some recent work in this that might be interesting. And then the complex geometries aspects, which we haven't really done much on the operator learning side, but we've done some work on pins that can translate to operator learning. So if there's any strong preference, I can focus on a single thing instead of giving you like, a mash of everything, or I can just, give you an overview of those topics tomorrow. Yeah? Yeah, those two things go hand in hand.